My name is Ofek. I'm a PhD student in the group of Professor Shlomi Reuveni from the School of Chemistry in Tel Aviv University. And today I'm going to talk about my recent work, which is title is given in here. But before we start, let me just thank the organizers for this amazing opportunity. And on a more personal level, I want to thank Dr. Arnapal, who was a postdoc in the same group in which I'm doing my PhD today. And from the first day, I think he was not only a group member for me, he was a mentor and he was a good friend. So I want to thank him for that. And I also want to thank him and his students, VK and Arup, for the amazing hospitality here in Chennai. So now we can start. So let me give you an outline, a brief outline of this talk, so just to get everyone up to speed on what we are going to discuss today. So today I'm going to introduce the Sokoban random walk. What is the Sokoban random walk? This is just a model for random walk in disordered media with tracer media interactions. I'm going to use this model that I've developed with my PhD advisor to show you how this interaction, the introduction of these interactions, is going to lead to a significant deviation from a simple random walk model in random environment, which is the anti-L.Bonomo. And then I will dedicate the rest of my talk to show you how to use or utilize a scaling approach to estimate the MSD of such random walker. So let's start, and I will start with explaining what random walks in disordered media are. So consider the following two-dimensional arena. So this is the arena, and we have a simple random walker starting at the center of this arena. What do I mean by a simple random walker? This is just a random walker with equal probabilities of going up, down, left, and right. But now there is a catch. Here you can see that we have these black tiles, and these are just tiles which are occupied by some obstacles. And we scatter this obstacle with some fraction rho. So in order to understand the dynamics of a random walk on such an arena, let's take a look at the two extremes of this model. So on one extreme, we have density which is 0, meaning that all the sites on this arena are accessible to our random walker. And in this case, we have free diffusion. This is pretty simple. On the other extreme, we have density which is equals 1, meaning we cover with obstacles the whole arena, and now there is no room for the random walker to move, and in this case we have a constricted random walk. The question now is what happens in the gray area between these two extremes. So luckily for me, luckily for us, 50 years ago, Pierre-Gilles Lejeune, who is a Nobel Prize laureate in physics, he posed this question and also gave an answer to it. And he did it using the anti-L.Bonomo model. So what is this model? Well, we have L.Bonomo, of course, which is just a two-dimensional arena covered with obstacles with some initial density rho, and we have this ant, which is basically just a simple random walker starting at the origin of this arena. And now we ask ourselves, how can we calculate the MSD of such a random walker? So let's, in the light of the previous slide, let's take a look at the two extremes. So one extreme is the extreme of low density, and in this case we know that we have free diffusion, right? So if we look on the left, this is just a plot of the square root of the MSD as a function of the time or the space. And as you can see, for low density, we just gain a straight line, meaning we have a free diffusion. Not surprising, everything is known. The second case, the second extreme, is the extreme of high density. In this case, we know that we are constricted to the origin, and in this case, as you can see from the plot on the left, we saturate to some saturation level. I think what is beautiful in this model is that we have a sharp transition between the constraint dynamics to the free diffusion dynamics, and it occurs at a critical density given in here. For those of you who are familiar with percolation theory, you can recognize that this is just the the complementary density to the percolation threshold, the well-known percolation threshold. And why is it just the complementary density? Is that because in percolation theory we assume that the density is with regard to the number of available and unoccupied sites. However, in my model, which I'm going to show you in a second, I refer to the density as the density of the occupied sites, so the unavailable sites. So this is why we have this complementary. Okay, so this is the model, and the basic assumption of this model is that our random walker is significantly smaller than the obstacles occupying the arena. Why is that? Well, I showed you that there are no interactions in the model between the obstacles and the end, meaning that the obstacles in this model are static. So this can only be achieved when we have a really small end. However, this assumption is not valid when we consider random walkers which are on the same length scale of the obstacles, and in this case we should assume that the obstacles are in fact mobile. So this is, I think, the basic motivation of why to account for mobile obstacles, and if you are not convinced by that, let me just show you a video from an experiment conducted in the group of Professor Yael Roichman from Tel Aviv University. Here you see a random walker, or a robotic random walker, walking around in an arena filled with cubes. And as you can see, this random walker actually pushes boxes away or obstacles away. And in this model, or in this system, we cannot use the anti-L.Bonomo model to try and calculate the MSD, because as you can see, there are interactions. So to account for these interactions, let me introduce the Sokoban random walk. So what is the Sokoban random walk? And here is just a simulation of this walk. We have three basic rules. The first rule is the same rule as we had in the anti-L.Bonomo model. We can always hop into an unoccupied site, which is pretty simple, right? The second law, this is the part where we introduce the interactions with the between the tracer and the media. As you can see, now I can also hop into an occupied site as long as the next site is unoccupied. And in this case, what do? We just push the box or the obstacle one site forward. Note that this is not possible in case we have two obstacles just joined together. So this is the model, and now you maybe ask yourself, why do you call it the Sokoban? Well, this is just an homage to a well-known video game from the 80s, a Japanese video game called Sokoban. You see, these are the same rules basically. So I'm using video games on my job. Nice. So this is the model. And now I need to try and convince you that there is a significance to the introduction of these interactions. And how do I do that? Let's compare on the MSD level the Sokoban random walk and the simple random walk, or the anti-L.Bonomo model. And we start with densities above the percolation threshold. So here are results taken from a numerical simulation. All I do, let's take a look on the plot on the left. All I do is to calculate the MSD. This is just an ensemble average, and I plot it as a function of time, or the steps, for both the simple, the anti-L.Bonomo, and the Sokoban random walk for three densities which all are above the critical density. And as you can see, both models attain a saturation level which is finite, meaning that they are getting confined. This is not surprising because this is a well-known result for the anti-L.Bonomo. But what I want you to note is that the Sokoban for any given density is actually attaining a higher saturation level, meaning that the Sokoban actually ventures farther away from the origin compared to the simple random walk. And I think that if you look on the right, this is just an example for just one realization or one trajectory of a Sokoban random walk plotted on a simple random walk, and you can see how it illustrates the results that the Sokoban ventures farther away. So I think now it's the point in the talk that you look at me and you ask, why do you give this talk? Because this is pretty obvious, right? If I can push boxes or push obstacles from my way, I can venture farther away, right? So it's not really interesting, right? It's not surprising. You could have thought about it yourself. So the point is, in order to, say such a bold claim, we also need to check what happens below the percolation threshold. So this is what I did in here. Now I'm going to show you trajectories of a Sokoban random walk for a density of 0.4, which is below the percolation threshold. So here is the trajectory after 10 to the power of 5 steps, 10 to the power of 6, 10 to the power of 7, and I think, first of all, this is really beautiful, and you also see the evolution in time, okay? But now I'm going to show you what happens after 10 to the power of 8 steps. Long animation. So yeah, now you can see that these two images look identical, and it is not like they only look identical, they are identical. So on the left hand side you see the trajectory or the visited sites of a Sokoban random walker after 10 to the power of 7 steps, and then you see the same trajectory just after 10 to the power of 8 steps. And if there is no change in the trajectory, it means that our random walker in this specific realization is constricted, okay? So once again, you may look at me and say, okay, this is just one realization, this may be just a fluke. You cannot say anything from one single trajectory about the whole MSD or the ensemble average, right? You need to calculate or to look at the ensemble average as a whole. So this is what I did. So here I'm going to show you numerical simulation for the MSD or the square root MSD of a simple random walk and a Sokoban random walk. And look and behold, this is what is going on. 3 things to look at. First of all, here I'm plotting the square root MSD as a function of the density, the initial density of the obstacles. And as you can see that for densities above the percolation threshold, what we get, as we've seen before, is that the simple random walk, or basically the Sokoban random walk, outperforms the simple one, or the anti-L.Bonomo model, in terms of the MSD. I actually ventures farther away, and we've seen it. Second of all, I want you to know that when we approach the percolation threshold, the simple random walk or the anti-L.Bonomo is approaching infinity, and this is not surprising thanks to the Gen, right? The surprising part, and this is where I come, is the fact that below the percolation threshold, while the simple random walk is at infinity, the Sokoban random walk actually attains a finite MSD. What does it mean? It means that for any given density in here, the Sokoban random walk is end up constrained in a finite cage, which is surprising because looking just at the densities above percolation threshold, we did not expect that, right? We thought we will get a higher critical density compared to the simple random walk. Okay, so now we need to explain the results, and this is where I pay another homage now to De Gennes, who was an expert on scaling theory, and I'm going to use a scaling approach to solve this problem and calculate this square root MSD. And how do I do that? First, we need to understand what is going to be the jamming condition. We realize that the Sokoban is going to end up constrained. Now we need to figure out what is the condition for this jamming or constraint. So let's take a look at the following simulation. Again, a simulation of a Sokoban random walk pushes things away. In blue, I just color the trajectory, and in a second you're going to see how this Sokoban random walk is going to cage itself in a finite cage. And I want you to look at it and think whether you can come up with some sufficient condition for the caging of this random walker. Just a hint, look at the depth of the layer that is constraining the random walker. A hint, it's not a single layer, but a double layer. So we are going to use now this knowledge in order to derive the condition, the jamming condition. So on the left, this is the configuration I've shown you before. On the right is the same configuration, but now I mark in green the perimeter of this walk. So let me explain. In purple, this is just the trajectory itself. In green, it's the perimeter of this trajectory, but it's not a single layer perimeter, but a double layer perimeter. Why do we need this double layer perimeter? Because if we have only one layer perimeter, the random walker can just push the layer forward and keep on moving on, right? So there's no jamming. I can still move forward. That's why we need a double layer perimeter in order to get jammed. So this is the realization. How do we write it down? So this is the condition, and I will explain. So think about the configuration on the right, but now we need to think about what does it look like at time 0. So at time 0, we have number of obstacles inside my area, which is just the size of my area, times the density, the initial density, right? This is the number of boxes. How do I get stuck? I need to take all the mass from inside the area and push it outwards towards the perimeter. When I do that, and I fill all the empty sides on the perimeter, which is just the perimeter times 1 minus rho, because I want them empty. So when I fill all the gaps, I create a double layer from which I cannot penetrate and get farther away. So this is the condition. How do we utilize it? This is very simple. So just for convenience, let me just denote R infinity is just the limit or the saturation level of the MSD, of the square root of the MSD. And this is just a one-dimensional scale of our configuration. Now what I do, I want to understand how both the area and the perimeter scale. So here from the simulation, I plot the mean area and the mean parameter for the ensemble as a function of this rho R infinity. And as you can see, these the dots are taken from simulation. As you can see, they follow a nice power law. So I can write this power law for the mean area and mean perimeter. I can get from the data, I can fit them into a linear line, and I can get the following values for alpha, beta, A, and B. And as I want you to note, we get powers which are non-integer, meaning that we end up with an area and a perimeter which are of fractals. So let's finish the calculation. So now we take our condition, we substitute the scaling laws, and we get the following formula, and this explains beautifully the result, because as you can see now, R infinity, the MSD, is explained by the initial density and by two parameters, C and gamma, which are given by the scaling laws. So as you can see, for any density larger than 0, we always end up with R infinity, which is finite, meaning that we are stuck in a confinement, which is very surprising, but also explains beautifully the results. Let me just finish in a second. So we just take the parameters that I've showed you how we get, I plug them in, and now I plot them together with the numerical results. And this is what we get. So here in dashed line I get the scaling. This is the scaling that I've just shown you. And in yellow you've seen this is a simple random walk, and in purple this is the Sokoban random walk. You see there is a great match between the scaling law I've gave you and the numerical results, which are independent. And I also want you to know that in grade area here, this is just a margin of 5% error. So from the dashed line upwards, it's just an overestimation of the parameters by 2.5%, and below it's an underestimation of 2.5%. And as you can see, the data falls beautifully inside this 5% margin. And just to sum everything up, today I showed you that short-range tracer media interactions are often neglected by people because they believe that they are not significant to transport properties. However, I hope that I was able to convince you that even if we introduce very weak interactions into our model between the tracer and the media, we get a totally different behavior. Above percolation threshold, we get that the Sokoban random walk ventures farther away compared to a simple random walker, and below the percolation threshold, everything changes. The simple random walker has a critical behavior, while the Sokoban random walker will always end up confined, which is really surprising. If you want to read this manuscript with all the results, all the figures, and much more, this is the archive submission, hopefully to be published very soon. And if you want to play the game, you can find it in here. And thank you for your listening.
Thanks. We have time for a few questions.
So if you can go back to your few slides, and when you're comparing your data with this one.
Yes.
This shaded area is somehow your data falls always below this dotted line. Is there some reason for that? It is not. Is there some systematic error that is creeping in?
Okay, this is a good question. I mean, we are just trying to figure out the point. I don't think I still have a concise an answer to it. I figure that it comes from the fact that we need to get even lower densities in order to catch the fractal the fractal dimensions correctly. The problem with going beyond 0.33, for example, is that you need to simulate the Sokoban random walk on matrices which are of size of 1,000 over 100,000 over 100,000, and you need to do it for at least 10,000 matrices. So we have two supercomputers in the lab, and they work non-stop on this simulation, because unlike percolation, you cannot run it deterministically. You have to run it in real time.
Yeah, I have one more question. So let's see. If you have these obstacles, and does obstacle shape matters? Because in reality, let's say if you have a square versus circular obstacle, and then if you have a particle which is scattering through, you can get into a stage where, for example, square can lead to some sort of a bound orbit, where it doesn't basically pass through, it won't diffuse anymore. And for the circle, it will diffuse always. So it depends. So basically, the obstacle surface, whether it's flat or carved.
Okay, so this is a really good question again. Again, this is I think we've sent it to review just 2 months ago, so everything is still fresh. But regarding to your question, we did try different geometries. We tried triangles, and we tried hexagonals. We see the same results over there. We did not try circles. We should try. You are correct. We also tried, I didn't have time to talk about it today, we also tried Cayley trees, for those of you who know Cayley trees, because percolation is exactly solvable on this topology. It turns out that the Sokoban is also exactly solvable in this case, and there's another surprise. Invite me to another talk, we can talk about it then.
Yeah, I have just 2 short questions. So,
yes.
What is the scale over which things need to be pushed to get jammed? So basically, you showed us the scheme. I mean, some picture, no? That.
Yeah. So I think the figure you're looking for.
No.
Just a sec. I think this one will because.
Okay.
You see that it's around for density of 0.45. It's around 10 to the power of 5.
So it should scale with the obstacle density, no?
It should scale, yeah. And this is what you've seen in the last. Okay. So this is basically the scaling law that we got. This is the answer. You see that we only depend on the initial density of the obstacles, and these 2 parameters which just come from the power law scaling of the area and perimeter.
And what happens if you change the rules of the game? I mean, you have shown us a specific rule.
Okay, so I think the only rule that constrains us right now is just the number of obstacles that you can push at a time, because if you think about the Gen model, basically there you can just walk onto empty sites, right? Here you can also do another thing. The next level will be pushing 2 boxes at a time, 3 boxes at a time, etc., etc. We did not try that yet, on a full scale. But from the preliminary results we get, we see the same. We see the same behavior. I believe that we will get the same result, but now the powers will be a little bit different, and the scaling will be different. But this is going to be of the same functional form, I believe. But we should still check it.
Hi, very fascinating work. I have 2 questions basically. One is a follow-up to Pinaki's question also. But before that, you do not implement periodic boundary conditions in this, right? Because in the Sokoban game, there is no PVC.
So to answer this question, it's not because of the game.
No, I mean, yeah, of course.
But no, we're doing serious physics in here. No, I did. What we did in here, well, when you work with the percolating system, in order to get the critical density, the right, the right evaluation, what you need to do is to look at the very large systems in order for the random walker not to run away out of the system. So you need to simulate very large systems. So when you do absorbing a boundary, it may be a solution which can save the data, but we wanted to start first of all with comparing to the most basic model, which is this 50 years old anti-Labyrinth model. But this is also a good point, what happens in a periodic boundary. I don't know how it is going to compare.
Right. And just a follow-up to that jamming question, what happens when a particle, when it walks into this, say, environment where it can no longer push around? Does it just walk back to where it came from? So is your walk self-avoiding, or can it like just hover in that spot for a few steps, or must it come back immediately afterwards?
Okay, so this is also a good point. Thank you for mentioning it. So each and every time step, I need to decide on which direction I'm going to. I will always make a step. At each and every time step, I will make a step, and of course I will only make the legal step. So, and if you think about it, there's no scenario in which I cannot take even one legal step.
So if there is no other step to go around, it will just follow back where it came from.
Yeah, because this is for sure will always be the possible step, right? I can always go.
But then you don't associate any kind of time scaling to this process. Like it could take, like in real time, it could be a longer duration than what it came back from. Because ideally if something goes into a trap, it will interact with the environment and like to be there because it's probably the most energetically favorable state. In that sense, I was asking actually.
Yeah, so in this sense, we really use just real time, and we didn't try to scale it. Maybe it's also a good idea. But
I would like to ask more questions, but maybe later.
Sure.
Any other?
So in the game that you showed, there were some immovable boxes also, and there were some movable boxes. Have you tried them with some kind of a relative density between these antenna labyrinth and your movable boxes?
Okay, now it's not working, but okay. So here you said that there are cases which the boxes are not movable, right?
Yes,
so
like the walls.
Yeah, so it happens also in the simulation, right? There will be scenarios in which I cannot push any boxes around. So, can you take
like an immovable box?
So you say a priori I'll just say, okay, this one is immovable. Okay, guys, this is an amazing question. I didn't have time to look at everything, but it should also be interesting because by doing that you can actually direct the random walker in a certain direction. And if you remember this guy, you see that when it walks around, it creates tunnels which sometimes are indestructible or very hard to destroy. So I believe it will go on the same line as this guy, that you create you just create some kind of tunneling, and which directs you in some direction. But we should also look at that as well. Thanks.
Any other? So, can I ask a question?
Yeah, sure.
Yeah, so you mentioned that close to jamming you have this two-layer structure. Mm-hmm. So it's not clear to me like why, because I thought that depending on that environment there can be 3-4 layer also, right? 3 layer also.
Yeah.
Most of them I agree will be 2 layer, but.
So what we did here is to just try to come up with a sufficient condition. Of course, that if I have 3 or 4 or 5 or 20 layers, I for sure cannot run away.
No, so I'm not talking about the rules. Mm-hmm. So I'm talking about that final structure that you get.
Yeah. So the point there is that because I can push one box at a time, the least restrictive condition for which I'll for sure be jammed is a two-layer. I need to create a two-layer, right? So you wanted to come up with a sufficient condition. Of course, it's a stronger condition. You can come up with other conditions which are more case-specific, but we try to make sure that we demand the minimum, but we make sure that we are stuck. Yeah, basically, but you can also require more and more levels. That's true.
This is in 2D, right?
Yeah, this is in 2D.
So things change in 3D, I suppose.
We have 3D. We have 3D. Again, not much time, but we have 3D. Different thing happen in 3D. Again, every topology we get different results, which is quite amazing. I won't spoil you what happens in 3D, but something a little bit different. The dynamics are different because of the fact that the work is not recurrent in 3D. So part of the fact that you jam yourself is that you need to return to the same place every time and push another box and another box to create this confinement, right? But in 3D, because you're not recurrent, you can just get lost and forget about the confinement that you created, and you just move away. But so there, the dynamics is a little bit different. Hope to finalize this part as well.
Okay, so let's thank the speaker once again.
Thank you.